Hi, Science 20s or Science 30s. Sorry, I'm making a lot of videos here. Science 30s. Mr. Riley here. We're going to be talking about electric fields today. So we already learned about gravitational fields. Electric fields are similar, but with one main difference. Like gravitational fields are produced by objects with mass, gravitational fields are produced by objects with charge. So you might kind of be thinking, okay, mass is something that we can all relate to, but what exactly is charge? So what charge is we don't notice charge because most things are neutrally charged. But if we think back to chemistry, we know that all matter is made up of atoms, and within an atom we have subatomic particles that are charged. And so we have protons in the nucleus of the atom, and then surrounding that nucleus, far away, we have electrons. These are the things that produce charge in objects. Usually we have the same amount of both, so things are neutrally charged. But electrons tend to be the subatomic particle that get transferred. And when we transfer electrons, whether gain or lose electrons, we can become charged. And this can happen a lot of different ways. It can happen by friction with static electricity. It can happen by a chemical reaction, like would occur with a battery or a cell. And it can also occur by something we're going to learn about called electromagnetic induction, which is something really cool. Like mass is measured in kilograms for us, charge is measured in a unit called the coulomb. And what a coulomb is, it is an amp of current per second. And we're going to learn about current and amps a little bit later on in this unit. And the big difference between a gravitational field and an electric field is in an electric field, the force that's produced can be attraction or repulsion. And with gravitational fields, it's always an attractive force. So there's a little something that we call the law of charges. And you guys probably know this. You may have heard the saying that opposites attract. And it's exactly true when it comes to electricity. So if we have like charges, they don't like each other. Okay, they are going to repel away from one another. And if we have charges that are opposite, okay, those two charges are going to move towards each other. They love each other. And so that would be an attractive force. So keeping that in mind, let's take a look at this problem here. So we're going to do a calculation. Now, we need to go into our data booklet, and we're going to find what we're going to actually find here is we're going to find that the formula here actually looks very familiar to us. So it's this formula here. So we have capital E. Notice it has that little arrow that signifies it's a vector. So it could be, a repulsive or an attractive force, but it also has these lines around it. So it's absolute value. So anytime we get an electric field strength value, we can just put it as the positive terms. And so we're going to have a constant like we did with gravitational fields. We're going to have the charge, and we're going to have the electric field strength. And then from the last formula, same thing, we're going to have R. So R is our separation distance between objects. So let's go back over here and let's take a look at an example here. So we want to find the magnitude of the electric field at a point 0.450 meters. Okay, so that's our R value. That's our distance from a 5 times 10 to the negative 6 Coulomb charge. So let's see what we have and what we need. So we have R, 0.450 meters. We have coulombs here now. So what measurement is coulombs? Coulombs is Q, and that's from your data booklet, you guys. You have to go and use that as reference. So 5.00 times 10 to the negative 6 coulombs. And then one thing I'm going to also need is K. K is the constant. So our value for K is 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. Looks very, very similar to the gravitational constant that we learned. And what we're trying to find here is we want to find the magnitude of the electric field. And so that's going to be our big E that we're going to be looking for. So let's get our formula here, and then we're going to plug everything in. So electric field strength equals KQ over R squared. I'm going to start to plug things in. So we're going to have 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. And then we're going to have our Q, which is 5.00 times 10 to the negative 6 coulombs. And then on the bottom, we're going to have our R value, so 0.450 meters. That always has to be in meters, you guys. So you may have to do a conversion. We're going to square that value. So we're going to take out our calculator, and we're going to see if we can find that value here. So, oops. So we're going to do, open up a bracket here, 8.99 times 10 to the 9. We're going to multiply that by 5.00 times 10 to the negative 6. You can close that bracket, divided by, open a bracket, 0.450. That's our R value, and we have to remember to square that value. We're going to press enter, and we're going to get this number, 221,975.3. So 221,975.3. And if we look at our formula here, we're going to be able to get our value for our units. So meters squared is gone. So I'm going to end up with newtons over coulombs. So that's my units for electric field strength. So for every coulomb of charge, how many newtons of force is the object going to experience? And we're going to have to put this into scientific notation as well. And how many sig digs do I want here, kids? Okay, I want to have the same number of sig digs as the least precise value from the question. So I'm going to have 3 for both of these, so 3 sig digs. So I'm going to use these 3 digits, 221. I look next door, that's going to have to round up. So I'm going to get 2.22 times 10 to the 1, 2, 3, 4, 5 newtons per coulomb. And that is the value of my electric field strength. Okay. So that's how you calculate electric field strength. Very similar to the other formula that we did, and we'll take a look at that again in a sec. So we also may have to draw electric fields. So with gravitational fields, the arrows always go towards the mass. In this case, you could have a positive or a negative. So these vectors always go away from positive and toward negative. Okay, so that's just something that's not in your data booklet. That's something that you need to remember. Now, if I have 2 objects interacting with each other, like these same charges, okay, 2 positive charges, these are actually going to repel each other. And so we're going to see, I'm going away from positive. So we're going to see something kind of like this happening. And all of these arrows are going to be pointing away from the positive charge. Of course, if I had a stronger field, I would have, or more charge, stronger field, I would have more lines. Now, in this case, these 2 objects are going to be attracted to each other. So they will actually have connecting field vectors here. And so we're going to see something, I don't know, kind of like this. And it's always going away from positive and towards negative. Okay. Now, we've looked at gravitational fields and electric fields, and we notice the formulas look almost identical. And there is something to that. So there's a question here: how does R, or the separation distance between 2 objects, affect the field strength? And I mean, I think we kind of know. We can think of, what happens to gravity when we get far away from Earth and we go into space. The gravitational pull on you is going to be less in space as you get further away from Earth. So as R increases, field strength decreases. But there's actually a sort of a mathematical way to look at this, and it's called the inverse square relationship. And so it would look like this. So we'd say the field strength is proportional to the inverse of the separation distance squared. So 1 over r squared relationship, or an inverse square relationship. And if we were to graph this, it would look like this. So as the separation distance increases, the field strength decreases exponentially. So we get that sort of that shape on that graph. Now to look at it in another way, so let's say we have a charged object, and this charged object at a distance of 1r, or one unit of distance, or whatever, we're just making it up. Let's say there's a field strength of 10 newtons per coulomb. And at 2r, what we're going to do with that 10 newtons per coulomb is we're going to multiply that by 1 over r squared. And r is now 2, right? So now we're looking at 2r. So it's basically going to be times 1 over 2 squared, or 1 over 4. So 10 times 1 over 4 is reduced